Alright, so I graded question 1 and 3. Question 1 had some things like P is you have the flu, and Q is you miss the final exam, and R is you pass the course. Yeah.
Do you want me to give a scene now before you talk about that? So that was John.
Oh, yeah.
Okay.
All right, thanks.
Before you give all the answers then.
Yeah. So when you have something like these are propositions, they're declarative, they're either true or false. And when you have something like P arrow Q, the best way to translate that into words is if P, then Q. Okay, if you have the flu, then you miss the exam. And if you get too conversational, you risk tripping over the imprecision of the English language. So if P or not Q, then not R. That's the precise way to translate that. But you can do that verbatim, say if you have the flu or you miss the exam, then you do not pass the course. But you can start trying to bundle those together and say you'll fail the course if you're sick or you miss the exam. And to us that's equivalent, but I would prefer you take these and really just plug them in. But it's useful to think about what these things mean. And we'll look at an example of that in a second. But the one thing that some people had some difficulty with was something like this. This is another proposition. It's the proposition that you have the flu or you miss the exam. And there's no if-then in here. Okay, it's just P or Q, this or this. So the last part of this I think was this. Or did I not have arrows in there? I think these were just conjunctions. Was that the question?
Yep.
I don't want to boot up my laptop. So this is saying you have the flu and you miss the exam, or you don't miss the exam and you pass the course. So if we think about the meaning of that in terms of semantics, what is this actually saying? Is it saying you have the flu?
No.
No.
It's saying if you have the flu.
It's saying, if you have the flu, are you going to miss the exam?
There's no real if-then there.
Yeah, it's not actually saying that. Because for this statement to be true, this could be true, or this could be true, or both. It may be that this is false. It may be that this is false. It's possible that you don't miss the exam and you pass the course. I think this was an and also. It's possible you miss the exam and you fail the course. You don't miss the exam and you still fail the course. But this could be true. You have the flu and you miss the exam. So if you're translating these things into English, don't get caught up in sort of the English way of soup or salad, right? Where we assume it's one or the other, right? It could be soup and salad.
Should start demanding the waiters use XOR.
Yes, exactly. Start throwing Latin at them.
That'll go well.
Yeah, yeah. All right. And then question 3, not a whole lot of issues there. So this was looking at quantifiers. So there exists an x such that x cubed equals -1. And this is all for integers. Right, this is clearly true. All we have to do to show it's true is find 1x. And we can say x equals -1, and that satisfies it. So that's true. There exists an x such that x to the 4th is less than x squared. We just have to find 1x, but we can't. Right, 0 is not less than 0, 1 is not less than 1. 2 will certainly be greater than, 2 to the 4th will be greater than 2 squared. And any number bigger than 2. And for negative integers, the square and the 4th are exactly the same as the positive. So this is going to be false. We can't find an integer that satisfies that. For all x, -x squared equals x squared. And that's true, that's algebra. If we pick any integer, it's negative squared. Well, this is just -1 squared times x squared, which is just x squared. So that's true. And then for all x, 2x bigger than x. And that actually turns out to be false. And why is it false?
Negative integers.
Negative integers, right? We're assuming that 2 is greater than 1, but if x is less than 0, 2x will be less than 1x. All right, and we had talked a little about question 2, and I didn't grade that one, but this proof that prove that this is equivalent to P and Q, or not P and not Q. And most people did this with a truth table, and that's fine. If you think about this logically, this is saying if P then Q, and also if Q then P. The only way both of those can be true is if both P and Q are true, or if both P and Q are false. If one's true and the other is false, then when we go in the direction where the if false then true, that will be a violation. So logically this makes sense, but this is saying if P then Q, and if Q then P. All right, see you. And if you look at the truth table for these implications, if the hypothesis is false, the conclusion is irrelevant, the statement's true. If the hypothesis is true, conclusion is true, this is true, and this is false. And so this is equivalent to P and it's equivalent to not P or Q. if P is false or if Q is true. So this is equivalent to not P and Q, ended with, or ended with not Q or P. Yeah?
Okay, if P is false and Q is true, then if P then Q is true?
Correct.
But that doesn't make sense with the second one because it would be false.
What's going to be false?
If and only...
This is not an if and only if. This is just an if. Right, so we can put that this is an if, this is an if. So I've broken the biconditional into two if-thens. And then substitute it in, so this is P then Q, this is if Q then P. And now you just do some algebra. You can distribute this over these two terms. So it's not P or Q, ended with not Q. And that's all ORed with not P or Q, ended with P. So I'm just distributing this over here and here and ORing those two. And then you can distribute again, this or this, ended with this. This is not P and not Q. ORed with Q and not Q. And then that all gets ORed with this, which is not P and P, ORed with Q and P. And Q and not Q is false. P and not P is false. And when you OR with a false, you just get your original. So this is actually not P and not Q, ORed with Q and P. And you use commutativity a couple of times and you can make this look exactly like that. The other way that Sage was just alluding to is we could actually write a truth table for if P then Q and if Q then P. And this will clearly be true, this will clearly be true, but this will be false because we know P then Q is false. And this will be false because Q then P will be false because Q is true and this is false. And then we can show that this truth table corresponds to this, which it does. This is just an exclusive NOR of P and Q. So P and Q have to be both true or both false. So that's kind of a hybrid of truth tables and logic.
So this is exclusive NOR, right?
That's an exclusive NOR, correct. All right, we did 4 and 5 yesterday, the logical expressions with Attack of the Lizard People and the even integers. 3, 1, 2, so that's that. So questions on any of that? This podium gets crazier and crazier. Every now and then I go wild and I just throw everything away or pile it in the corner. So some people asked about practice questions. If some of this stuff is elusive still, how can you work on it and get better at it? And the textbook actually has lots of questions. So right now we're this stuff last week, Chapter 3 Logic. There's a bunch of exercises throughout, but also here at the end, that you can work on. Construct truth tables for these expressions, express these statements in symbolic form, insert parentheses, lots of basic truth table, logic statement manipulations, write the negation of these statements. Right, so these are propositions, write the negation of that proposition in English. Proving some identities. Use truth tables to prove these identities.
How do we know if the answers we know about it is correct or not?
Feel free to ask.
There's no answer key in the back of this.
I don't think there's an answer key.
There is for odd number problems.
Oh, really?
Oh,
Okay,
yeah.
cool.
Cool.
Awesome. So yeah, so some of these arguments, like the attack of the lizard people question, right? Where you're given propositions and asked about the truth or fallacy of other statements. 3.7, I think, is induction, so we haven't done that yet. But some of these other ones translate these sentences into expressions. All fish except sharks are kind to children. And so on and so forth.
The book gets sarcastic. It's hilarious.
Yeah. It's an intense book, and you never make money on textbook writing anyway, but doing it as a labor of love, I can imagine your mind wanders at times. So don't hesitate to go through there and look for questions to work on. And like I say, just ask, right? In the beginning of class and ask if there's any questions. Yeah, I was looking at questions such and such in the text. Can we talk about it? Absolutely. Right? We've got time in here. I'll fill in the time, so we won't have any dead time. But there's a lot of things that we don't have to necessarily cover in this course to give you a good background in discrete structures. So I'm very happy / prefer in some ways to spend that time going over particular issues. Right? I'd rather you nail a set of key concepts and be really rock solid in those, then sort of brush over a larger set of concepts, but have them all kind of not really gel. So the time's available for that.
What would be the change in the truth table if it was if and only if?
This column here is if and only if. That's what a biconditional says.
Okay.
So if P then Q, and if Q then P, that's the same as P if and only if Q.
Okay.
Can you modify that truth table for, like, say, question 5, either as even or odd, and have that work, or so false would be odd and true would be even?
So maybe you could have P be the proposition that n is even, and Q the proposition that 7n plus 4 is even. What would that do? We could... That might be an interesting way to get to visualize a solution. You still need to do some legwork underneath, though, to fill those in, to see what those 4 cases would be. But there may be something to do with actually just filling in evens and odds. I haven't thought about that. But yeah, maybe there's a different way to do this modular arithmetic like that.
I was thinking of, instead of mu Q, just add n, and have n be true or false, and then you have on the other 2 tables, 2 sides, which in this case is n is even and 7n plus 4 is even.
Right.
When you go through that, you technically go through every possibility with that.
Right, so you got 4 cases. Yeah, you could do that. Cool. Other questions? All right, so keep working logic stuff if it's not ringing quite true yet. So we've been talking about modular operations, and we can say things like 17 is congruent to 2 modulo 3. And we started talking about Fermat's little theorem yesterday. But there's a punchline to all of this modular stuff. If we're working modulo some number, we can do algebra, arithmetic, multiplication, things like that, over this smaller set of values. This small, what we call a ring of integers. And for example, if I know 17 is congruent to 2 modulo 3, I know 17 squared is going to be congruent to 2 squared, which is 4, and I know 4 is congruent to 1 modulo 3. So with almost no work, I know the square of 17 is much more than a multiple of 3, without ever having to compute that. And if I know 17 squared is congruent to 1, I know 17 squared to the 100th power is congruent to 1 to the 100th power, which is just 1. And 17 squared to the 100th is 17 to the 200th. So if I multiply 17 by itself 200 times and subtract 1, I know I've got a multiple of 3. Again, with almost no work. So we can use this ability to manipulate things that might be computationally intractable and make statements about them by doing relatively simple operations. We can also deal with the totality of the infinite set of integers, in some cases by reducing it to a small set of integers in some modular system. For example, a number is even if and only if it's divisible by 2, congruent to 0 mod 2. And equivalently, n is odd if and only if it's congruent to 1 modulo 2. So, if n is even, prove 7n plus 4 is even. Well, if n is even, n is congruent to 0, 7n is congruent to 0, 7n plus 4 is congruent to 4, which is congruent to 0. We're done.
Wait. Oh, okay.
If n is odd, n is congruent to 1, 7n is congruent to 7, which is congruent to 1. 7n plus 4 is congruent to 1 plus 4, which is congruent to 5, which is congruent to 1, so 7n plus 4 is odd. And we can do even more general things. If n is even, n is congruent to 0, any multiple of n is still going to be congruent to 0. So any multiple of an even number is even. If if n is odd and k is even, then k times n is a multiple of an even number. So that's got to be even. So an odd number multiplied by an even is even, and an odd number multiplied, an even multiplied by an even is even. But if n is odd and k is odd, n is congruent to 1, k is congruent to 1, n times k is congruent to 1, so the product's odd. So even times even is even times odd is even, odd times odd is odd. And that's kind of cool. The last digit of a number is just what that number is congruent to modulo 10. If you look at the remainder when you divide by 10, that's the ones digit. Does that make sense? Because all the other weighted components are just multiples of powers of 10, so they're all divisible by 10. So 57, I know immediately it's congruent to 7 modulo 10. Okay, that's almost a definition of the ones digit, the last digit on the right. So any integer is congruent to one of these 10 things modulo 10. It's got to be, right? There's only 10 things you can be congruent to. So n squared is congruent to either 0 in this case, 1 in this case, 4 in this case, 9 in this case, 16, 25, 36, 49, 64, or 81. Which is 0, 1, 4, 9, 6, 5, 6, 9, 4, or 1, modulo 10. Meaning that the square of any number must end in one of these digits, because it's congruent to one of those quantities modulo 10. So n squared must end in either 0, 1, 4, 5, 6, or 9. Which was a problem we did with a lot more work the other day. So that's part of the power of working in a modular system. We can take an infinitude of possibilities and reduce them to a finite set of possibilities. And then we can do exhaustive things like this. Exhaustive meaning going through all the possibilities, not just that it tires us out. I'm just going to say positive to simplify things. Let n be any positive integer. Well, we know that we can write n as the following sum. Powers of 10 multiplied by digits. Right, this is the decimal expansion of a number. So if n equals 5-digit number with 5 digits, D4, 3, 2, 1, and 0. That means n is equal to D0 plus 10D1 plus 100D2, and so on. We're just expanding a number. So the number 147 equals 1 plus 4 times 10 plus 7 times 100. So we're just interpreting what it means when we write this thing out in decimal. Is that confusing?
Is
I
that
think you have it
backwards?
backwards, because you have 1 plus 4 times 10.
I do.
Okay,
Because that's
Thank you.
741, right?
yeah.
Okay.
Yeah.
Hey,
There
good
we go.
question.
Two pen strokes. So if we look modulo 3, n is congruent to this sum modulo 3. Well, what is 10 congruent to modulo 3? It's congruent to 1. What is 100 modulo 3?
1.
It's 1. It's 1 more than 99, so it's 1 times D2. What's 1,000 modulo 3? Right, what's 10 to any positive power modulo 3?
1.
It's going to be 1 because we know 10 is congruent to 1. So 10 to the k is congruent to 1 to the k, which is just 1. So our number is congruent to just the sum of the digits. So in particular, n is congruent to 0 mod 3 if the sum of the digits is congruent to 0 mod 3. If and only if. So here's your basic trick for telling if a number is divisible by 3. Add up the digits. If the number you get is divisible by 3, then your original number was divisible by 3. Otherwise, it's not. So 123,450,918. I can tell you immediately that's divisible by 3. Because the sum of this will be 6 minus 15, 24, 25, 33. That's divisible by 3. Pop it in your calculator. I'll pop it in my calculator. One, 2, 3, 4, 5, 0, 9, 1, 8. Divided by 3, yes, 41,150,306. The universe still works. And when you're adding these digits, I can say 1, 2, 3, that's 6, so I can ignore that. 4 and 5 is 9, I can ignore that. 9, 1, and 8 is 9. I don't have to actually add them up.
Is that true for all numbers?
That's true for all numbers. And there's a lot of properties like this. You can find divisibility by, I think, 11 by adding the even and the odd digits and seeing if their difference is divisible by 11. Something like that.
11
You
is
can do it with 9 as well, I know that.
And you can do it with 9.
9. Yeah, 9 adds up to 9. 11 goes like 1, 2, 1, 1, 2, 3, 2, 1.
Yeah.
Goes like that. But there is something for 7.
There is a 7. And I don't remember what it is.
Yeah, it's just kind of harder.
But you can look these up, or you can play around with a decimal expansion like this and see if you can discover properties. So these are ways you can do like quick arithmetic sometimes. Whenever I get a number like a student ID, my brain always tries to see if it's divisible by 3. If it's not, then maybe it's prime. But almost all the time it's divisible by 3. Yeah.
One for 7 is if you, to find a number is divisible by 7, take the last digit, pull it, and subtract it from the rest of the number. If you get a number divisible by 7, including 0, then the original number is divisible by 27.
So add the digits, but subtract twice the
It
last
says
one.
take the last digit, double it, and subtract it from the rest of the number.
Oh, cool. Okay. So,
And it says if you don't know the new numbers divisibility, then you repeat over and over and over again. So in that case, you take the 1 off, you have 1,001, you double it to get 1,002. Take the, subtract it from the rest of the number, you get 998. You get 998 is divisible by 7.
Oh, okay.
No idea.
interesting.
It seems inelegant.
So it's a recursive kind of.
Is there, can you find these rules for divisibility by a certain number?
Yeah, you can probably find them on Wikipedia.
Yeah,
I mean,
that's
like,
where I'm finding
I was
it.
Okay.
thinking more along the lines of can they be found like from a mathematical standpoint?
I don't know. I'm sure people have explored this, but I haven't.
Yeah.
But if you start taking this expression and evaluating it in different moduli, module 3, 5, 7, and so on, you may find some patterns that you can then extrapolate without actually working through individual numbers.
Because I feel like it might make it easier for like primality testing.
Yeah, yeah. And the rule for divisibility by 5, we already know, right? Because 10 is congruent to 0 modulo 5. So this and this and this and this and all these other terms will be congruent to 0. So their sum is congruent to 0. So n is just congruent to whatever that rightmost digit is. And the only digits that are divisible by 5 are 0 and 5. So if your number ends in 0 or 5, it's divisible by 5. Otherwise, it's not.
So you were saying earlier you can find the prime number by seeing if it's not divisible, or not divisible by the modulus of 3.
Well, you can hope that it's prime.
Hope it's prime.
You can dash those hopes quickly by finding it's divisible by 3, which always seems to happen to me. So, I always wanted like a patent number that was prime. So when the patent would come out, I'd like really quickly check, and they're always divisible by 3. It should only happen a third of the time, but I don't know. It happens way too often. All right, so modular arithmetic lets us do good things, and it lets us do things with some applications we'll get to Monday finally, like generating parity bits. When you're transmitting data and you want to know if there was an error in your transmission, we can generate a bit by using modular arithmetic. Using hash functions, which we talk about in 222, where you want to take information and store it, but you want to store it in a place that you can find quickly. Instead of just storing it somewhere in an array and searching through the whole array, you can say, if this piece of data is stored in this array, I'm going to find it at this location. And now you just have to check that location and see if your data is there. That's a hash function. Really efficient time-wise, and that's based on modular arithmetic. ISBN codes, UPCs, all of these things, these codings, these barcodes that you see and such usually have check digits built into them. Credit cards do MD5 hashes, things like that, and those are based on variants of this. And encryption, which we still are going to talk about on Monday, is based on lots of modular operations, but we're working over a reduced set because we're in this modular ring. So let me talk a little bit more about some of these details. Actually, let me back up and give you one other algorithm that you're going to need for one of your homework questions, which are posted. And that's this question of greatest common divisor. So when we have a fraction a divided by b and we want to simplify it, if the top and bottom are divisible by 2, we can divide them by 2. We get a smaller set of numbers. To reduce a fraction as far as possible, you want to divide by the largest denominator in common between these two expressions. So, for example, 80 over 20, that's just equal to 4. 90 over 20, we would divide by 10, and we'd say this is 9 halves. This factor that we're using to divide these down, that's called the GCD of these two numbers. And there's a systematic algorithm we can use to find greatest common divisor. And it works like this. So you have two numbers, 90 and 20. Let's just deal with positive numbers for now. And let's suppose the first number is bigger. So what you can do is you can write 90. See how many times 20 goes into it. It's 4 times 20 plus a remainder of 10. So write the larger number as a multiple of the smaller number plus a remainder. Now take the 20 and the 10 and do the same thing. 20 equals 2 times 10 plus 0. Once I get down to a 0, this is my greatest common divisor. So, if I wanted the GCD of 45 and 6, 45 equals,
Five, 9, 5, 3, 2.
I think 7 times 6 plus 3. 42 plus 3. 6 equals 2 times 3 plus 0. There's my GCD. About 735 and 252. So 735 equals, I think I can multiply this twice. I cheat with my calculator. Plus 231. And then 252 equals 1 times 231 plus 21. And then 231 equals 11 times 21 plus 0. There's your GCD.
9, 10 times 3 plus 45 is not 7 times 6 plus 2.
Say what? 25 is not 7 times 6.
45.
Oh, it's not? 7 times 6 is 42, plus 3 is 45. Yeah. Don't scare me, man.
So you're just trying to find like the biggest common denominator, and then you're just carrying that through.
Yeah, you're
Trying
fine.
first pick the first term that you're looking for, then the second term you're looking for, and in the case of 231, you're just finding what's common.
Yeah, so now we find the GCD of this and this.
Reminds me a lot of the arithmetic you do to find binary numbers.
Yes. Yeah, very similar process. And you can convince yourself that this works by playing around with modular expressions. We're trying to find something that divides both of these. And anything that divides 735 and divides 252 has got to divide their difference. So the GCD of these two numbers has to be the same as the GCD of these two numbers. That's really all that's going on. And every time we do this, we get things that are smaller than this. So in no more than 734 operations, we'll get down to a 0. It's usually a whole lot less. And if you do this with prime numbers, 47, 13. 47 equals 3 times 13, that's 39, plus 8. 13 equals 1 times 8 plus 5. 8 equals 1 times 5 plus 3. 5 equals 1 times 3 plus 2. 3 equals 1 times 2 plus 1. 2 equals 2 times 1 plus 0. There's your GCD is 1. Because nothing divides a prime except it's all in 1, so 2 primes, they're going to have a greatest common divisor of 1. And in this case, we say that these two are relatively prime. But there's a more general definition. All right, so that's how you find greatest common divisors. And there's a homework question that has you do that for a few half dozen different cases. A few million cases.
Well, it shouldn't take long with this technique, so.
Yeah, it's good practice. All right, so we'll talk about modular exponentiation on Monday, which will set us up for doing those applications. And then probably Tuesday, I want to go back and pick up some things that we've skipped from earlier chapters. I want to talk about functions, summations, and matrices. And we're not going to do a lot of detail on those, but I want to make sure you've seen at least the terminology. And I'll throw some homework questions at you about those. And then we're going to go on to talking about mathematical induction, which will be like, for me, I think it's the coolest part of the course. So that's our program for next week, and then we'll just go on from there and go crazy.
We haven't gone crazy already.
No, we haven't really started to go crazy yet. We're hinting at it.